that we face is, for instance, when we put our footing, so there's our footing, and we like to find a sand or a gravel layer to put the footing onto because it reduces our settlement. So we can put the footing at the top of the sand layer, for instance, and we avoid that clay, and then we're worried about settlement caused by this particular clay, for instance. And if we put it on the sand layer, the sand layer sort of acts as a base for our footing. So it's a common situation. But what we're worried about is, how thick does that sand layer have to be to make sure that we don't get a bearing capacity failure. In other words, what we're afraid of is that this footing is going to punch through the sand layer into the clay. Because let's just say this is a soft clay, for instance. And, okay, so how do we analyze that, or how is this typically analyzed? Because we want to, in other words, if I put my footing here, well, and I do my bearing capacity calculations for that sand, I might not get the right answer because that sand is not thick enough. We're gonna get this punch through. So, how do I figure this out? Well, people have observed this, and what they find is that the thing doesn't punch straight down. It really, if you tried punching through, it spreads out at a 2-to-1 ratio. So in other words, I get this region here that would fail that would actually punch into this clay layer. Now, because of this 2-to-1, and sort of a rule of thumb, because this is 2-to-1 on that side and 2-to-1 on that side, then what happens is that we can calculate this width, and that width ends up to be the width B plus the height of the sand, or the H of the sand, thickness of the sand. So the way this is typically analyzed, a little bit conservative, but is that we take this, and instead of analyzing this, we analyze this. So in other words, if you look at this is B plus the H sand, and so we have a footing here that is based in the clay, and so because we're worried about failure in the clay. So, in other words, the B in our bearing capacity equation becomes B plus H sand. So in other words, we don't analyze this, we do analyze this. So that's the way we're going to handle this. Now, what is that? How does that work? Because if we have a really thick sand layer, then that's good, and that makes our B plus H sand bigger. So it has that effect of sort of accounting for the thickness of the sand. The greater the thickness, the bigger the B, and the more stable the situation is. So, and that's what we would expect. In other words, if we have a really thin layer of sand, then this H sand is going to be very small, and basically the B is not going to be very big on our clay. So, so that's how this works, is that it sort of it takes into account the thickness of the sand. In other words, if we have a thin sand layer, it's not going to do us any good. But how thick do we need? And this is the way that we figure out how thick is going to work for us. Same thing if we have this situation where what do? We take our piles, we put our piles at the top of the sand layer, basically. And we use the same approach, the B plus H sand. How thick is the sand layer going to be that's going to help us? Now, in plan view, what does this look like? Well, this is our original B here. So there's our original B. And then when we do our B plus H sand, we get that. So when we figure out what our area is, for instance, it's going to be B plus H sand quantity squared is going to give us our area. So let me just emphasize that. So in other words, once we've done this and we recognize this, then we just go through our calculation the way we normally do, and we analyze the clay. So in other words, we don't use the properties of the sand. We don't use the properties of sand, we use the properties of the clay. So make sure that when you do your calculation, it's all about the clay. All we do is create the greater width. And everything else we've done now fits. So, okay, I want to just make a little comment here about expansive soils. It's a little bit off topic in a sense for a second, because a common problem around here in the Bay Area, for instance, is if we have expansive soils. Okay, so in other words, we'll say we're building a house on expansive soils. Well, interestingly, when I say expansive soils, what we mean by what can happen under certain circumstances is, for instance, if we have a dry clay. So this is unusual. We don't, in this class to this point, we haven't looked at dry clays or partially saturated clays. We always assume they're completely saturated. But what can happen is, certainly if you have clay at the ground surface, the sun beats down and dries out the clay, and it dries out, several feet of clay, or you can, a number of feet of clay can be at least dry-ish. And if we build our house, I say house because a house is a fairly light structure, and this dry clay then becomes saturated due to rain, then what can happen is that the clay expands, and it soaks up the water and expands. And what it can do is it can actually lift up the house. And of course, it never lifts it up uniformly. It lifts it up a little bit here and a little bit there and a lot there, and the next thing you know, you have your house all sort of cracked up. It's like a dry sponge. So if I were going to explain it to you, you've all had, on your sink, you have a sponge sitting there, and first it's wet because you've just used it. You set it at the side of the sink and it dries out. Well, what happens to it when it dries out? It basically shrinks down. Then when you wet that sponge, it gets bigger again. It gets bigger. So the same thing with this clay. It shrinks when it dries out, and then if it's dry and then you get it wet, it will get bigger. And so that's the concept behind it, in a sense. You can envision it with a sponge, and clay acts much the same way. So what is the solution? You don't want this to happen, so a common way this is done is that, in a sense, you need to have anchors. You want to hold the house down. So this is not how it's done, but in a sense, you want something like this, where you have these anchors here tied to the house, so that if this clay becomes saturated, then you're going to keep the house pulled down and hold it in place. And in addition, there are other things you do. You put space underneath here so that you're not lifting a slab, and so you have a crawl space underneath, and that those are some defensive measures you can use to keep the house in place. Now, this is a difficult thing to build, so instead of building that, what you do is you put in piles, basically, and they're deep enough so that this region down here is the anchor region, and so we've used these sorts of things in a sense with walls, with the anchored walls, the tie-back walls. You put your grouted rebar in there, and you can create an anchor here. So, and it works just as well as this if you get it in deep enough. So this is a common situation. You put in your crawl space, and this is a common solution to these problems. Now, I point this out because we're putting piles in the ground not to keep the structure from undergoing settlement. We're putting the piles in the ground to prevent the structure from lifting up. So, just another thing that you need to be aware of when it comes to foundations, and you may see this in any home that you've lived in or may potentially live in the future. Okay, so let me just go through this. We've already gone through enough walls and things. I'm not going to go through that. Okay, I want to make a comment, and we're going to do this problem, is how do we handle the bearing capacity of a mat rather than a footing? So in other words, here, the width of a mat is frequently quite big. So that if we, if we are looking at, a failure that takes place along a circular failure surface like that, then we're going to go down a deep distance. In other words, the width B and the depth to the bottom of the circular failure surface would be the same. So in this case, if we're 45 feet, I'm going down 45 feet. Well, if I do that, I'm most likely going to contact a number of different types of soil, or and so I've got to, how do I use my bearing capacity equation when I have all these different types of soils? And it's, this is not the only failure surface, but this is a potential failure surface that you need to evaluate, and this is the way that I want to show it, because it has a lot of aspects of what we've been doing in terms of we need to figure out the resistance along this failure surface, and we need to figure out the soil strengths. And so this analysis is going to give you more insight into how we use the circular failure surface and how we get the strengths on those surfaces, on that surface at different locations. So, and this is an important aspect of failure analysis in geotechnical engineering. So, all right, so this problem is find the factor of safety at t equals 0 plus. Now, what does that mean? Of course, that means I've got my water table up here, for instance, but I'm going to be drained in the sand, drained in the gravel, undrained in the clay. So t equals 0 plus, we've got, so here are our soil properties. Now notice I've given you a K naught here. Why K naught? Because we want to know what the stresses are in the ground. And here I've estimated as being 1 minus sine phi prime. And we're not building any wall, so we don't have active and passive situation in terms of trying to figure out what is our tau FF in the ground. So, okay, so we've got our C prime, our Phi prime, and our SU or sigma prime I for this clay, and the K naughts are given. So, and the unit weights. So, okay, so what my goal is to find the bearing capacity, the factor of safety. And so what I want to do is I want to find tau FF at the points of interest. So what I've done is I've drawn the circular failure surface like that, and then I've broken it up into segments. Now, obviously, when you're in practice, the more segments you break it up into, the more accurate in a sense is your calculation. So, but I kept it reasonably simple. So, but I've broken it up into 6 segments: 1, 2, 3, 4, 5, 6, and we're trying to get the tau FF on each of those surfaces. What is going to be the strength at each of those surfaces? So, what I want you to notice is, and the way that we're going to do this is that in this region here, the failure surface for 1 and 2, the failure surface is close to being vertical. At 3 and 4, it's still close to being vertical. Just to keep it simple, we're going to take it as being vertical. But in 5 and 6, the failure surface is closer to being horizontal, so we're going to take the failure surface in those regions as being horizontal. That's going to have an impact on determining what our tau FF is. So the way we're going to look at it, we're going to look at all the 6 points of interest, and we have our depths. So I'm not going to... you can use geometry, you can draw this to scale, it doesn't have to be exact, but you can get those depths of those points there. And then we're going to calculate out the sigma V at each of those points. Now, notice that we have the pressure bulb from our structure looking like this, for instance. Let's draw it like that. And so we're going to say that points 1, 3, and 5 are within the pressure bulb, and points 2, 4, and 6 are outside the pressure bulb. So when we calculate out our sigma V, we need to come up with the pressure bulb factor at points 1, 3, and 5 in order to get the sigma V. Whereas the other 3 points, we just are going to use. So let's look at 2, 4, and 6. What do we have? 2, 4, and 6 is depth of 5 times 120, 4, 10 times 120 plus 10 times 100, 6.6, 10 times 120 plus 20 times 100 plus 7.5 times 110. Why? Because it's out here. Our sigma V is out there. But for the 1, 3, and 5, I've got to do, 1, I've got the same as 2, but then I have to add in the pressure bulb factor times the weight of times the Q for the structure. Again, the pressure bulb factor times the Q for the structure, and then the pressure bulb factor times the Q for the structure. So you got to put in your pressure bulb factor. The Q for the structure here is what? The weight of the structure is 3 million pounds. The B is 45, so it's 3 million divided by 45 squared. So, okay, so we've been able to determine the sigma V for each of these points. So eventually, we need to get, now notice we're assuming that we need to get our U's. So I have a UXS, a U water table, and a U. So what's my UXS? Well, For the sands and gravels, it's going to be 0. Oops. So sands and gravels, it's 0. Because, no U excess in those. Underneath the structure at point 3, well, I get a U excess due to the weight of the structure. So I'm going to have, it's the pressure bulb factor here, is going to go in here. And so we get our U excess. And our U water table is obvious. So we get our U's. And then, sigma V prime is what? Sigma V minus U. So we get our sigma V primes. Now, this second table, so all I've done here is I've moved that to there. So that column to that column. So I'm just rewriting that for the sake of making it clear. Now the question is, I've got my sigma V prime. Do I need my sigma H prime? Well, yes, I do for 1 and 2 because I have nearly vertical failure surface, and for 3 and 4, they're also vertical, but we're going to use our SU in that region, so we don't really need it. Okay, so because it's clay, I don't need it because I'm going to be doing my total stress analysis in the clay, whereas in the sand and gravel, I'm going to do an effective stress analysis. So this is vertical, so yes, we need sigma H prime. This we're saying is horizontal, so I don't need sigma H prime. So in other words, sigma H prime, why do we need it? Because I need to get the normal stress on this vertical plane, and that's sigma H prime. I need to get the normal stress on this plane, and that's sigma H prime. So whereas here, the normal is, well, it's close to being vertical, so I just need sigma V prime for the others. So, yes, we need sigma H prime for 1 and 2. No for 3 and 4 because we're going to use SU. And no for 5 and 6 because the failure plane is horizontal. So I get my sigma H prime. How do I get it? I use my K naught there to get my sigma H prime. And then I want to get my tau FF. So that's what we're going for here. All this work to get the tau FF. And how do we get it? Well, we're going to use our failure envelope. So if you remember, the failure envelope for sand drained is what? Looks like that. That means that my tau FF is sigma prime tangent phi prime. It's sigma prime tangent phi prime, but it is, depends on that sigma prime could be sigma prime H or it could be sigma prime V, depending on the orientation of our failure plane. So sigma prime tangent phi prime for the sand and gravel. For the clay undrained, it looks like this. So I just want to get my SU. So sigma H prime tangent phi prime, sigma H prime tangent phi prime gives me my tau FF in that sand. Sigma V prime tangent phi prime, sigma V prime tangent phi prime in the gravel. That's what I want because, again, in the gravel it's horizontal, and so sigma V prime acts perpendicular to that plane. So I get my tau FFs for my gravel, get my tau FF for my sand. Now what do I do for the clay? Well, what do we do for our clay? I use my SU over sigma prime I, rather sigma prime I. So my sigma prime I is 952, and so I get 0.42 times 952. It's the same in both cases. In other words, there's no consolidation that has gone on because we're assuming that the building is put down instantaneously. So we haven't changed that. We have not changed the soil strength in the clay due to putting in the building. So I get 400 for both of those, and they're both at the same depth, right? The 3 and 4 are at the same depth. So they're both going to have the same strength. And now we have our arc length. What's our arc length? Well, I want to know what's my distance here. So what's my distance along this arc? And I'm not going to do the geometry, but you can draw it to scale. You can do whatever you want. But we get those arc lengths. And then this is the arc length. We're going to take 1 foot perpendicular to the paper. So tau FF times the arc length gives me the force, resisting force, along that arc. So this is, this is the hard part to get. That's pretty easy, and then we just multiply those out to get the force. So my total resisting force is the sum of all of these. You can notice that this quite a bit of resistance takes place in that gravel down there. Now, that's going to give us a clue that maybe this circle may not be the critical circle. So we're not going to go through this, but in a more advanced analysis, maybe that an arc that goes like that never gets down to this gravel may actually be the most critical. And you'd need to analyze that too. But right now, we're just going to stick with this circular failure surface that goes like that. But in practice, you have to look. This is one of the issues is you don't know where this is going to fail, and you got to try a lot of different things and look for the lowest one. Now, normally, a lot of ways this is done using computer program, but I want you to be able to do and understand where this all comes from and do some of this by hand here. Okay, so our resisting moment is going to be that force, the sum of that force times the 45 feet. So in other words, we're taking moments about where? We're taking moments about this point here. So 40, that's 45 feet everywhere. So that is our resisting. That's the moment arm. So our resisting moment that's the radius there. This is where I used it. And then I'm taking 45 feet perpendicular to the paper because why am I now taking 45 feet perpendicular to the paper? Because I'm going to assume, and this is not is that I'm taking in a three-dimensional picture. Maybe I can draw this. I don't know. But I'm taking a slice that looks like this. So in other words, I'm getting failure. It's hard for me to draw underneath it, but this is the weight of my building here, and my resistance is all along here. Oops. And this distance here is 45 feet perpendicular to the paper there. So I want to include that because I'm assuming this, not exactly realistic, but somewhat, is that my failure surface in 3D looks like that. So, yeah. And so I get a resistance of 308 million pound-feet, which is 308,000 kip feet. The moment due to my structure weight is 3 million pounds, 45 over 2, because we're assuming it acts down the middle. And that gives me 67 million pound-feet, which is 67,500 kip-feet. I divide those two, and I get a factor of safety of 4.56. So that is how you handle multiple soil types. And like I say, other failure surfaces may be more critical, and you need to evaluate those as well. And given this particular situation, yes, it's probably going to be more like something like that. With now we're looking at one way to analyze. You have the center of your circle, your slip circle or failure circle, is someplace else. It's not down here, and then you have to take your moments in a different way. We're not going to get. It's just geometry, easily done. If you work at it, I mean. Now, okay, same problem, but how do we handle it at t equals infinity? So same problem, everything's the same, all the soil properties are the same, all this stuff is the same. So what I've shown here is now we have to do what? Now we have clay drained. So it changes it doesn't change anything in the sand. It doesn't change anything in the gravel. So in other words, all of these sands and gravels and sand and gravel calculations are all the same. So that doesn't change because we're still drained in the sand, drained in the gravel. So the only things that change are, in the clay here, and, many of the calculations are identical. But what I've done is the modifications are in orange. So look at the orange here. So orange. And what do we see? Well, UXS is 0 because it's drained. Okay, so at this point here, there's no UXS anymore because it's at t equals infinity. And so that's going to change my U. It changes my sigma v prime. And so that changes the sigma v prime. And now we're saying that, yes, this is approximately vertical. So now I do need because, that's approximately vertical, and I have to figure out my normal stress there. So the normal stress is going to be a sigma h prime. And so I now use my K naught and my sigma v primes to get my sigma h prime. Once I have my sigma h prime, then I need to use my failure envelope for my clay drained. And if you remember, the failure envelope for clay drained is what? It's this one. And the tau ff is C prime plus sigma prime tangent phi prime. And so that is the C prime plus sigma prime tangent phi prime. So we're using the clay properties here. And what does that do for me? That means that the arc length is the same. I multiply the arc length times the tau ff, I get that. And now I'm getting more resistance in my clay, which makes sense because it's been consolidated and stronger and that sort of thing. And so I just add those numbers, multiply by the 45s, and here's my resisting moment, same calculation. My factor of safety has now gone up a little bit. So that's how you handle the bearing capacity with a deep failure surface that goes through multiple soils. Okay, just a couple practical things here. And that is that, you can see a bearing capacity failure every time you step on the beach. So, in other words, each time you step on the beach in dry sand, you make a little bearing capacity failure. How does that look? Well, here's your foot here on the side view. And let's look at the back view. Well, what happens? You step on the beach and your foot sinks in, right? And if you look, you get a little pile of sand on the outside. And the sand goes up. So you're getting a little bearing capacity failure there. Now, if you step on a humped area, what happens? Well, you get a failure like this. And you can see that that the shear surface is not as big here, and you're going to, so if you step on a hump, you're going to get a very easy bearing capacity failure, which makes sense if you've ever, as you're walking on the beach. On the other hand, if you step into a depression that may be somebody else's previous footprint, for instance, then what happens is what? Well, we would get a failure surface that looks like this, but notice we have our Q outside, that Q that holds it down. And so you're less likely to get a failure if you step into a depression. And you can try this out on the beach, and it's what you observe. So this fits our bearing capacity theory with that Q that gives us more resistance for our bearing capacity. Okay, so this is just a little thing that you can observe when you're walking on the beach and understanding bearing capacity a little bit more. Now, let me just, and this should be up here. Notice if you walk on the beach, not in the dry sand, but in the partially saturated sand, so you walk around where the waves are splashing, but not completely saturated, what do you find? Well, you see that. Why do you walk there? Why do you walk there? Because the little capillaries, the water, in a sense, connects the sand particles. Those little capillaries pull the sand particles together and create some effective stress at the boundaries between those sand particles. And as a result, it makes the sand stronger. So you're less so if the sand is stronger because you get that effective stress caused by those capillaries, then you get a much stronger sand, and you walk there, you don't have these bearing capacity failures all the time. So that's why you walk there. You can tell that to your boyfriend or girlfriend or whatever when you're walking along the beach. You're walking in that region where it's just partially saturated because you get those little capillaries, which increases the effective stress and makes it less likely, increases the strength of the sand and makes it less likely to have a bearing capacity failure. I'm sure your friends will love to hear that story. Anyway, okay, I want to say just a little bit about the islands in the delta. You've probably heard about these, and I want to contrast them if you're not familiar with that area. Here's a normal island. A normal island is what? This is water, and then we got our island here. That's what we always think of when we think of an island. Delta is different. The islands in our delta, the so-called islands in the delta, are, put little quotation marks, islands in the delta. They're a little bit different in that the island is, yes, dry and there's water around it, but the island is down low. It's below the water. In other words, the water's here, and the island is down here. That's where it's dry. And why is it dry? It's dry because there are these levees that sort of act as dams around the island, and then they can farm here. They can't farm here because it's wet. So they have the levees there to in order to create this dry island so they can farm in it. Well, here's the problem is that if these levees break, the water comes in and you no longer have an island, you can no longer farm there. So that is the issue. These levees are very big, and if there's just a break one place in the levee, is that levees or dams, these are not engineered dams. They're not, there's no spillway, there's no powerhouse or anything like that. These are just, in a sense, they're not well engineered. They may be a little bit, but not much. Piles of dirt that have developed over many, many years. And as a result, they can break. It's a problem, and there are miles and miles and miles of these things. So I just sort of describing this so you have an idea about it in case one day you're working on a project that has to do with stabilizing these levees so that they don't cause a failure and flooding of an island. Okay, let's see what I have here. All right, I'm going to stop there.